Alrighty, my guys, it's time to finish off this AP chemistry nonsense. Let's do it, okay? The test is coming up on Thursday? Yeah, Thursday. It'll be epic, don't worry. Not this Thursday, okay? Don't panic. It's starting next Thursday, don't worry. Hello, everybody, I'm Karar, and today we're going to be tackling Unit 6, Thermodynamics, and it's kind of a fun chapter, not gonna lie. Also, I've looked into what I've not covered yet, and basically, the two videos I called tip videos are literally the full units for both Units 5 and 7, so I'm not going to make completely new videos for those because that would just be the exact same thing again. So what I'm going to do is I'll rebrand those as unit reviews because they basically are unit reviews. And then there's some things in kinetics I didn't cover, so I'll make that into a part 1 and part 2, and we should be Gucci. Alright, let's talk about thermodynamics. Dude, I trolled and I covered a bunch of the thermodynamics nonsense in the previous video, the Unit 3 walkthrough, but I'll teach all the new stuff in this one. So the best way to explain thermodynamics is to talk about it in the laws of thermodynamics. Wow, that's not expected. What, you explain something using its law? That doesn't make any sense. But you know, I'm the kind of guy who likes to go against the grain, so we're gonna explain it in terms of the laws, okay? Because no one has done that in the history of the universe. So the first law, or in fact, we can start with the Zeroth Law, okay? Zeroth Law of thermodynamics basically says that if one object is in thermal equilibrium with another, basically that means that if you touch them, no energy is transferred, or no net energy is transferred, and that basically means they're the same temperature, so they're the same temperature. Then if the second object is the same temperature as the third object, then the third object has the same temperature as the first one. Now you might say, that's really obvious. Why the heck would they make a whole other law for that? That doesn't make any sense whatsoever. Well, the law basically only says that if 1 is in equilibrium with 2, and 2 is in equilibrium with 3, then 1 is in equilibrium with 3. It doesn't say anything about temperature. But it allows us to define temperature, right? Because now we can define temperature as if they have the same temperature, they're in thermal equilibrium. So basically, Zeroth Law of thermodynamics is why you're allowed to assign temperatures to things. Or why temperature is a measure of whether things are in equilibrium with each other. But honestly, this one's not that relevant for the AP exam, so we're not going to talk about it much more than that. Alright, first law of thermodynamics. The way I remember what this one is that it's like the most basic, fundamental thing in the universe. Conservation of energy, okay? You probably learned this in every single class you've ever taken in your universe. So, this is basically conservation of energy. And that's pretty self-explanatory, right? You can't create or destroy energy. Well, Einstein said you could, but you know what? We don't care about Einstein. Einstein's a meme, okay? Einstein's not a true... Okay, I'm sorry. Einstein's my guy, don't worry. But basically, the main way that AP Chem makes you apply the first law is in the equation U is equal to Q plus W. Sorry, delta U. So this basically applies for gases, and this is where we're going to use it the most, right? So basically it's saying the change in energy of your gas is equal to the heat that you add to your gas plus the work done on the gas. Makes sense, right? If you do work, it gets more energy, right? If you add heat to it, it also gets more energy. So your overall change in energy is how much heat you add plus how much work you do on it. The main tricky part about this is deciding when Q is negative, when Q is positive, when W is positive, when W is negative. So Q is positive when work is being done on the gas. The way I like to remember it is like, when will your internal energy increase? It'll increase when you add heat to the gas. So if your internal energy is increasing when you add heat, that means your Q is positive when you're adding heat. In negative, you're taking away heat, so your energy should decrease. That's why it's negative when you're taking away heat. Same thing for work. If you punch a ball, right, it's going to start moving faster, right? And you're doing work on the ball. So basically, if you're doing work on an object, it gets more energy. So if work is being done on the object, then its internal energy increases, so W will be positive. Let me just write it out. So positive, add heat, and do work on. Okay, so the one last thing you gotta know about this equation is that work is equal to P delta V. Now, this is more used in physics. Honestly, in chemistry, it's not that useful, but if they ever say, like, the gas expands from, like, 0.5 liters to 1.5 liters, and the pressure stays the same, then you just multiply the change, which is 1 liter, times the pressure, and you're good. Now, another quick way to calculate delta U is equation 3/2 nR delta T. Now, I haven't seen a question on the AP exam that ever asked for this kind of thing, but like, I think you might as well know it. It's a pretty useful equation to know. It also makes a lot more sense why your internal energy only depends on your temperature and how many moles you have. So this equation is more for logic. Alrighty, so now let's talk about what enthalpy is. Enthalpy is literally just your internal energy. It's basically the same thing. Now, technically, it's internal energy plus the product of pressure times volume, but you could literally think about it as internal energy and you'll be fine. So enthalpy is like written as H It could also be written as Q. So the first thing we're going to talk about is like enthalpy if we think about it as Q. And the one application of this is called calorimetry. Basically what it is you take a cup, you have water in it, and then you add something to it, like a salt or something that dissolves, and then you can measure the change in temperature of the water to see how much energy was released. So let's do an example, right? Let's say you add like 1 gram of like NaCl, and you add that to 100 grams of water, right? And let's say that the water changes by 2 degrees Celsius after we add in the NaCl and it completely dissolves. Let's say a positive 2 degrees Celsius, so it increases in temperature. Now, I really don't know whether NaCl dissolving is exothermic or endothermic, but I'm just going to say it's positive 2 degrees Celsius. That means that the NaCl released energy into the water, right? So that means that the reaction is exothermic. So let's explain this real quick. So exothermic means that the system releases energy. That means that the system itself is going to lose energy because it's giving energy off. So that means that your delta H, so your change in enthalpy, is going to be less than 0. Endothermic, on the other hand, means that you're taking in energy from your surroundings, so you yourself are going to get more energy. So your delta H is going to be positive. So in this case, clearly it's giving off energy, so it's exothermic. So how do we see how much energy is released? So basically we use specific heat. So we know that there's 101 grams of solution. Remember, always use the grams of solution when you're talking about dissolving something and measuring how much energy it has, right? Because the thing you put into the water is also at room temperature. So the reaction has to heat up both the water and the thing you put into it. So you got 101 grams, and then you got to multiply by the specific heat. And we could just assume that the specific heat is the same as the specific heat of water, because adding a tiny bit of solute did not change the specific heat of water at all. So this is going to be 4.18 joules per grams degrees Celsius. Then we multiply by 2 degrees Celsius, and hooray, we have our answer. Let us calculate. 844 joules. Now unfortunately, delta H has the units of joules per mole. Joules per mole. Or kilojoules per mole, but whatever. So basically, we have to first divide by moles to get our final delta H of the reaction. This right here is the energy released, but it's not the delta H of the reaction. So we find how many moles of NaCl, so this is just going to be divided by the number of moles, which is 1 over, sodium is 23, Cl is 35.45, and then we will see what this is equal to. 844 times 27 plus 23 plus 35.45 is equal to 49331, which is basically 49.3 kilojoules per mole. Epicness, okay, we did it. Let's go, nice. Oh wait, we made a mistake. Okay, so whenever you get an answer for delta H, always make sure you remember to put in the sign at the end. That's how I like to do it. I don't really worry about the sign before I get to the end. But we know that this is an exothermic reaction, so our delta H should be negative. So we'll just add in the negative sign right now. Alright, so this is our actual delta H. Epic. We did it. Now we actually did it. So now let's talk about Hess's law. So Hess's law basically says that like if you have a bunch of change in enthalpies, what you could do is you could subtract them or add them to get a new change in enthalpy. So for example, if I had like C solid plus like O2 gas yields CO2, and that has like A joules per mole of enthalpy change. And then the other one is like, what's another example? What about C solid plus O2 gas? Well, we gotta multiply this by 2, yield 2CO, gas. And this has B joules per mole. Then, if we wanted to like find out how you can make carbon dioxide from carbon monoxide, what we could do is we could subtract the two equations. So we literally just do A minus B here, and when you negate something, we're negating the second reaction, so we had to flip it. So now we have, instead of this, we get 2CO gas yields 2CS plus O2 gas. Wait, but 1 second, things don't cancel out. Our carbon is still there, so we want to get rid of the carbon. What do? We had to multiply the first one by 2. So we multiply this whole thing by 2, and then this becomes 2A. And then now we add it, and we get 2CO gas plus 2O2 gas yields 2CO2 plus O2. And then this becomes 2A minus B because we added the 2A here. And now we can cancel out an oxygen on each side. And epic, we're left with this reaction right here, and that gave us that the overall enthalpy change is just a combination of the other enthalpy changes of the other reactions. So what they like to do a lot is they like to give you two reactions, and they give you the delta H for each one, and they want you to find the delta H of a third reaction that they gave you. So let's try to define an example. Alrighty, so this is one example they might give, right? Alright, so the way I like to approach it is I like to see like for each of these things, right, for each of the things in the reaction we want to find, which equation are they in? So NH3 is only in the second equation. So we know for a fact that we have to bring this NH3 to the left side and we have to multiply it by 2 somehow. And the way we do that is we basically say that we take, let's call these A, B, and C first. We have to do negative 2B. The negative flips the equation and the 2 multiplies it by 2. So now we have a 4NH3 taken care of. What about O2? Well, O2 is present in 2 equations, so let's not worry about that quite yet. And O is only in the first equation, so we need 4 NO on the right side. It's already on the right side in this equation, so we gotta multiply by 2, so plus 2A. And now for water, the only equation that has it is the third equation, so we need 6, so then we gotta add 6C, because it's already on the right side, we just need to multiply by 6. And then this should give our answer, but if you guys wanna do it out, let's just see what happens with the other things. How many N2 do we have? So from the A we get 2 N2 on the right, on the left side. From B we get 2 N2 on the right side, and from C we get nothing. So they cancel out. Good. And you can do this for the rest of them just to check that they cancel out, but we're basically done here. Just calculate this out by plugging in these values. This for A, this for B, this for C, and you're good. Alright, now let's talk about enthalpy of formation. So basically what enthalpy of formation is the enthalpy change of the reaction of forming a substance from its element. So basically, let's take CH4, right? Methane. And methane is usually a gas. So it has to be formed from carbon and hydrogen, right? So carbon in its normal form is solid. Remember that the equation for enthalpy of formation has to be in the element's normal form. So it has to be carbon solid. If this is a carbon gas, it would not make any sense, and it wouldn't be the enthalpy of formation. And then the hydrogen is usually an H2 gas. So we balance this, put a 2 there, we're good. And basically the delta H of this reaction is going to be your delta H of formation, which is symbolized like this. Now another cool thing to know about enthalpy of formation, for elements, it's 0. If you think about it, that makes a lot of sense, right? Because let's say we put CS on the right side, then what is it made from? Its constituent elements. It's just made by itself, right? The left side is going to be the same thing. So your delta H is just going to be 0. Alright, so that's why individual elements in their normal form are always 0. So why is this useful? Well, let's say we had a more complicated reaction. What about combustion of methane? So plus O2 yields CO2 plus water. Let's balance this boy real quick. Alright, so we want to find the enthalpy change of this reaction. All we got to do is subtract the enthalpy of the formation. So we would take 2 times the enthalpy formation of water, and then we would add this one, so times 1 of the delta H for CO2, and after we've added in the products, we had to subtract the reactants. So minus 2 delta HO2, because it has a 2 over here, and then minus CH4. And usually they'll give you all these numbers, and then this is just equal to the delta H of the reaction overall. Nice! Now there's another way to find the enthalpy of reaction without actually knowing the individual heat of formation. We could use something called bond enthalpy. And that's basically the energy stored in a bond, right? Because it takes some energy to break a bond, right? And it also releases some energy to form bonds. The way my teacher explained it is like, if you want to break a board of like a block, right? You have to hit it with a karate chop. And that takes a lot of energy. So that's why it takes energy to break bonds. And then, like making bonds, it does the opposite. So it releases energy. So let's draw out the structures of these. So this is like CH single bonded. And then O is double bonded to each other. And then CO2 is like this. And then H2O is like that. So there's 2 of these, there's 2 of these, and then 1 of everything else. So in order to go from this side to this side, what we gotta do is we gotta break up these bonds. So we gotta break up 4 CH bonds, and then we gotta break 2 O bonds, O double bonds, and then we had to break 2 CO bonds, because there's 1 CO2 molecule, but within that 1 molecule there's 2 CO bonds, and then we had to break 4 OH bonds, because in each molecule there's 2 bonds, but there's 2 molecules, so you had to multiply that by 2, so 4 OH bonds. So we had to form these ones, we had to break these ones, and it costs energy to break these ones. So our enthalpy change is going to be 4 times the bond enthalpy of CH plus 2 times the bond enthalpy of O minus 2 times the bond enthalpy of CO minus 4 times the bond enthalpy of OH. The way I like to remember it is that bond enthalpy is really weird. You have to start from the reactants instead of the products. With everything else, you do products minus reactants, but for bond enthalpy, because breaking bonds takes energy, you have to start from the left and go to the right. And then the other step is just to make sure you know the Lewis structures and then be able to count how many bonds there are. Alrighty, we are done with enthalpy. Let us move on to entropy. It's gonna be so cool. Entropy is kind of epic, not gonna lie. So entropy is basically the measure of disorder of something. And basically what the second law of thermodynamics says is that the entropy of the universe is always increasing. Which always scared me. I was like, wait, if it's always increasing, are we all gonna end up as like blobs or something? Like just floating in space or something? But who knows? Who knows? So what exactly is entropy? So I just said it's a measure of disorder, but to make it more clear, think about it this way, right? If we have a solid ice, right? It has a crystal. So this crystal is really ordered. They're all in rows, nice columns, perfectly aligned, everything's Gucci. But when it becomes a liquid, everything's just sliding past each other, right? So clearly a liquid is way more disordered than a solid. And when it's a gas, these guys are literally just running around. They don't care. They're just going haywire. This is like recess during not even middle school. We didn't even have recess then. Recess during elementary school, okay? So clearly, a solid is like a nice old high school classroom. Well, high school classrooms are not very orderly. But yeah, it's very orderly. But then as you go to gas, it has even more entropy because everything is just running around randomly. The other like definition of entropy is a state definition, which basically says the more possible states you have, the more entropy you have. So let's say we had two like gas chambers, right? And we had like two gas molecules, right? Then there's basically three positions it could be. That, or it can also be like this. However, let's try adding another one. Then there's these three options, but then there's another one. We can also have one on this side and two on the other side. So now, clearly, the three molecules have a lot more entropy than the two molecules because there's more possible options. These different things I'm drawing are called microstates, but they're probably not going to ask too much about that. So let us talk about how entropy applies to reactions, right? So let's say that we have H2O solid is melting into H2O liquid. And it asks you, what is the delta S of this reaction? How is the entropy changing? Well, as I explained before, liquids are way less orderly than solids, right? So they have a higher amount of disorder, so they're have more entropy. So if you're going from lower entropy to higher entropy, your delta S is going to be positive. Let us say that you go from like NaCl solid to Na plus Cl minus. What's the delta S of this? This is also positive because once you dissolve something, it's way less ordered. A crystal is way more ordered than a bunch of separated ions floating in water. What happens if you go from like, let's say that you have CH4 plus O2 yields H2O liquid plus CO2 gas. Well, basically, you're going from two molecules of gas to one molecule of gas and one molecule of liquid. Now, liquid is clearly more ordered than gas, so this is going to have a delta S of negative because it is decreasing in entropy. It's getting more ordered. And then one last example, why don't we have like, what's a good example? Haber-Bosch. So N2 plus 3H2 yields 2NH3. So as I explained before, more gas molecules means more entropy. So on the left side right now you have 4 molecules of gas, right? But then it goes to 2 molecules of gas. So your delta S is negative because you're becoming more and more ordered. Because as you decrease the number of molecules, you're becoming more ordered. Alright, that's all you gotta know for entropy. Let's talk about the last thermodynamic quantity, Gibbs free energy. Now, Gibbs free energy is like, the actual definition is like not that interesting, but the way I like to think about it is a measure of spontaneity. I have no idea whether I spelled it right, but this is not English, okay? I can spell it however the heck I want. So by spontaneity, I mean like if a reaction is spontaneous, it's just gonna occur without any input of energy. If it's non-spontaneous, that means that you have to do something in order to make it happen. It doesn't happen on its own, basically. So the one thing you gotta know about Gibbs free energy is that delta G, which is the change in Gibbs free energy, is equal to delta H minus T delta S. This is the one equation you gotta know, so know it, okay? Do not forget this equation. Honestly, this one you just gotta do a lot of problems, practice it, make sure you know it. Now, the biggest problem I've had with this equation is sometimes they give, like, Gibbs free energy in kilojoules per mole and enthalpy in kilojoules per mole. But then they give, like, delta S in joules per mole. So it's really annoying. You gotta convert everything to kilojoules or everything to joules. Don't forget to convert. I always just multiply this by 10 to the 3 so that it's converted to joules. I think it's a lot easier that way instead of dividing. And then this right here is the temperature in Kelvin. Oh, sorry, this would be joules per mole Kelvin, my bad. Alright, so basically this is just also a memorization thing. A negative Gibbs free energy means that it's spontaneous. It'll just happen by itself. Well, okay, the other way you could think about it, right? Delta S is generally a positive thing, right? By second law of thermo, a spontaneous process should have a positive delta S. Then it makes sense that as you increase the temperature, right, a reaction is more likely to occur, right? It just makes more sense. If your molecules are moving really fast, they're more likely to hit each other and do a reaction. So, increasing temperature will make this more negative. So clearly, spontaneity means that you're getting more negative because increasing the temperature makes this more negative, and it also should make it more spontaneous. And then delta G greater than 0 is going to be non-spontaneous. Alright, so now that we know what delta G means, we can also relate it to our equilibrium stuff. So let's say that delta G is less than 0, right? It's spontaneous. That means that if it's spontaneous, it wants to convert reactants to products. Because that's how a reaction works, right? That's what a reaction does. So if it's spontaneous, it just all the time, without any input of work, it just goes from reactants to products. So let's think about reaction quotient. What's Q again? It is basically the ratio of products to reactants, kind of. So if you say that your delta G is negative, that means you favor the product because you want to make more product. So then what does that mean about Q? Well, that means that right now your Q is too small and you want to make it bigger. If delta G is positive, right, that means that you don't want to go to the products. In fact, you want to go the other way. Like, the products are bad. We don't want to go to the product. So that means that your Q is way too big. You have way too many products and you want to decrease the number. So, that means that your Q is too big. Now, there's a specific equation that relates the two. So delta G is your Gibbs free energy change at this temperature. Then there's something called delta G standard. And that's basically your delta G at standard temperature and pressure. Then, basically, if we do minus RT lnq, we get this. Oh, sorry, there should be a plus right here. The reason why this makes sense, right, is if you increase Q, you get more products, right? And if you have more products, you want to make less of them. So, the reaction gets less spontaneous because you want to make less products. That's why this right here is a positive, and as Q increases, this whole thing increases, so your delta G will increase, making it less spontaneous. And also for R, always use 8.31 because for these kind of things, we always use SI units. And also make sure that this is in joules, not kilojoules. Okay, and then the other thing we could do is, when is it at equilibrium? Well, basically, equilibrium always occurs when delta G is equal to 0. So, if we say this is equal to 0, and then this is equal to delta G standard plus RT ln Q, well, what is Q at equilibrium? It's just equal to K. That's the definition of K. K is your Q at equilibrium. So then we get that negative RT ln K is equal to delta G standard. So basically the things to take away is delta G is 0 at equilibrium because you don't want to go more to the products, but you also don't want to go more to the reactants. The other takeaway is that as you get more products, your reaction gets less spontaneous, which is why as you increase Q, this whole thing increases, meaning your delta G increases. Alrighty, I think we are good. That is all I got to talk about for thermodynamics. Let me know if you guys want more of these videos. As always, if you enjoyed the video, leave a like, subscribe for more, all that good stuff. And I will carry out my master plan of rebranding the other two videos as unit reviews, because they basically are unit reviews, and then I will make a part 2 for kinetics soon. Don't worry. Alrighty, thank you guys for watching again. See you guys next time.